YouTube, but I will resolve them in parallel with the talk. So let me still announce it. I am very glad to present Dan Ciubotaru from Oxford and announce his talk on Dirac inequality and unitary representations.
Thank you, Dima. Thank you for the invitation. I'm very pleased to give a talk in your seminar. So I'm going to use my tablet and just write so that it's more like a board talk. So the goal is I want to present some results about the use of the Dirac inequality for the problem of classifying of the unitary dual of a p-adic group. So this is inspired by well-known all the results for real groups. So the well-known Bartasarati inequality that I will present in this setting, and then results of Vaughan, Salamanca-Riba, and other people, more recent results. And in my case, the main tool is going to be the Dirac operator for graded affine Hecke algebras. That I defined with Barbash and Peter Trappa about 9 years ago, 10 years ago. So I will try not to say much about the graded affine Hecke algebra. That's going to be sort of hidden in the proofs. But I will try to formulate the results so that they make sense in the context of p-adic groups. And because in order to do that, I will concentrate on unramified principal series of a split p-adic group. Even though the results are more general, so the results are more general. For example, whenever we know the Hecke algebra, or the endomorphism algebra, if you want, algebra attached to a Bernstein component. So, for example, a pleasant case that you can do with the same tools is the case of ramified principal series, where the results that we need are given by Alan Roche. But there are other cases.
Dan, when you say
okay, so now let me
series, sorry, can I ask a question?
Sure.
When you say unramified principal series, you mean all representations with the Iwahoe fixed vector, or
that's correct?
Okay.
Yeah, so all subquotients of unramified principal series. Okay, so now some notation. We have K, a non-Archimedean local field. then O, the ring of integers, and FQ, the finite field, finite residue field. And then I'll take G to be the K points of a split semi-simple group. And then fix a maximal split torus T and a Borel subgroup, and then associated to this, we get a base truth data. This is the based root data. In order to parameterize the unramified principal series, let me take T-check the dual torus, and then G-check. So I think of this as living inside G-check, which is the Langlands complex dual group. So corresponding to the dual root datum to R. And then T is the Liealgebra. T check is the Liealgebra. And inside there, I want to fix a real form. T check R. Okay, so now whenever we have S, an element in the dual torus, we can associate to it chi S, an unramified character of T, and then we inflate this to B, and then form XS, the unitarily induced from B to G of chi S. So this is the unramified minimal principal series. So as we all know, the category of smooth representations of complex representations of G is a product of subcategories, which are this is the decomposition defined by Bernstein. So these are the Bernstein components. And then there is this one component, so the unramified component. This has the irreducible objects are the subquotients of XS as S ranges over T check, but of course it's a classical result that the composition series factors only depend up to W action on S. So in fact, you can think of S as being a W orbit in T check. Then the question, which I won't be able to answer, but that's the motivating question, is what are the irreducible subquotients of XS, S in T check, that are unitary. Okay, so let me give you a quick example just to gain some understanding. So when G is SL2QP, then G check is PSL2C, and then T check is the diagonal torus, things like A inverse mod plus minus the identity. And you can decompose T check into the real part and the imaginary part. So the real part, this is isomorphic to positive real numbers, and this is isomorphic to S1, the polar decomposition. And then according to this, the unitary unramified unitary dual looks like this. So we have the real line, and then somewhere here I have the origin, so that corresponds to the identity element in the torus, and here I have P, and here P inverse. And on this real line, I have a complementary series around 1, which is unitary. So this is the complementary series. At P, I have the trivial as the quotient and the Steinberg as a sub, and that P inverse there the other way. And then at here I have S1, and there is one special point that corresponds to the element I minus I, and at that point the tempered representation splits into a direct sum of two irreducible tempered representations, and everything else is also unitary. So that's what the unitary dual in this Bernstein component looks like for SL2. But then after that, it becomes very complicated. And so what's known, the main results that are known, Tadic has done GLN and also inner forms of GLN, but I'm talking about split groups now. And Muich has G2. And then the other things that are known is the spherical unitary dual of split classical groups. That's for due to Barbash, classical, and Barbash and myself were exceptional. And then there is also the dual picture, also done about the same time, the Whittaker dual, which is due to Lapid, Muich, and Tadic. For classical groups. Okay, so there may be other results, but those are the big results. So, or at least some of the big results. And the problem is very complicated. If you want to get a complete answer, is very complicated. And what I want today is to tell you a small part of it that's easy. And more I want is, what I want is to illustrate this tool of Dirac inequality in this setting. So to simplify things further, I am going to concentrate on the real line or real parameters. So that I'm going to take nu, which is in the real form of this dual Liealgebra and take the corresponding S nu, which is the exponential, Q exponential of this, which is in the real part of the torus. And then I'll change notation and just call X nu to be X S nu. And now we think of nu in TR. Okay, so the classification of irreducible constituents of X nu, this is known by the results of Kashdan and Lustig. And it says that the irreducible ones are in one-to-one correspondence with G check nu orbits on G check 1 nu and irreducible local systems, equivariant local systems. So let's call this orbit something C, L, irreducible local system, G check nu equivariant local systems L on C, but not all of them, just so-called of Springer type. So I won't define this. And here G check nu is the centralizer in G check of nu, and G1 check nu is the +1 eigenspace of add nu on G check. Okay, so the classification is known. So which ones are unitary? Now, particularly interesting are the following parameters. So I take N check to be the nilpotent cone of G check, and then G check acts with finitely many orbits nilpotent orbits. If I have a nilpotent element, then by Jacobson-Morozov, I can form a Lie triple. Now, the type of parameters that I want to look at in particular are the ones where nu equals 1/2 H check, where H check is H check for some O check, where O check is one of these orbits. So these are particularly interesting parameters. Why is that? Because this type of parameters, they're closely related to the conjectures of Arthur. So in particular, what's known, this is by old work of Barbash and Moy, that the spherical constituent, so the K spherical constituent of X/2 H check O check is unitary for all O check, where here K is G of, well, O, sorry. This is the maximal hyperspecial. So,
excuse me.
yes.
What is the notation A check subscript O check?
That's just notation. Sorry.
Oh, that's the notation.
Yeah, because I want later on I will vary O check, so I just want to say which one.
Okay.
Yeah, sorry. Yeah, I should have said here. Sorry, O check is G check. E check. Okay. So then, still a difficult question, but a sub-question is what are the unitary constituents of such a varies over nilpotent orbits.
Then can I just ask about this result of Barbash and Moy?
Yes.
Was it proved by case or conceptually?
No.
Conceptual.
The conceptual proof. So if you're in the category where like this category, the unramified or Ivahori one, then you via the correspondence with Ivahori Hecke algebra modules, you can prove that the Zelevinsky involution takes unitary modules to unitary modules, because once you pass to the Ivahori Hecke algebra, this Ober-Zelevinsky involution gets mapped into the honest Ivahori-Matsumoto involution of the affine Hecke algebra. That one is easy to see that it maps unitary modules to unitary modules. So if you have a unitary equivalence between the Bernstein component and unitary modules for the Ivahori Hecke algebra, which you do in this situation by results of Barbash and Moy, then you know as a consequence that the Ober-Zelevinsky involution maps unitary modules to unitary modules. The AZ dual of the spherical constituent is exactly the tempered generic constituent, and that you know is unitary. So that's how the proof goes.
Okay, but the other result, I mean, is it case by case or conceptual? For the tempered. Oh, it's a tempered. Okay.
It's a tempered representation. Yeah. Okay.
It is in square integrable.
Yes.
Not only tempered, it's square integrable representation.
If O check is distinguished, it's square integrable.
And then it's just induced.
And otherwise it's just induced. Yes. Well, almost, yeah. There are also these elliptic ones, but that's okay. So now so what I will give you is an answer when O check is large. So I'll in some examples when O check is large. So let me tell you what the main tool is. So this idea of the Dirac inequality. So if I have V, let's say a subquotient of some x nu, then I can look. I have K, this hyperspecial, which has a pro-unipotent radical So I can take V upper UK, and on that, I then get an action of K mod UK, which is this K bar, and in this case is just the finite group, finite reductive group. So the Dirac inequality, the principle, I will write a precise theorem, but the principle is that the structure, let me introduce some notation. So let's call it res K bar V, this representation. So the GFQ structure of a unitary V puts a bound on how large mu can be. Okay, so I'll make that. So it will tell you the type of result that the Dirac inequality gives you is that if V contains a particular GFQ type, then, and it's unitary, then the corresponding parameter nu has to be less than a certain precise bound. The precise bound has to do with these half H's. So then the idea is that if you're out there if you're looking at some Satake parameter, this half H that's large, then there will be lots of constraints of what kind of K types the irreducible subquotient can have in order to be unitary. So that's sort of the idea, but let me make it precise. So now in our setting, in this unramified setting, the only irreducible GFQ representations that occur are constituents of the induced from BFQ to GFQ of 1, which are in one-to-one correspondence with simple H GFQ, BFQ, modules, which is the finite Hecke algebra. And this is a deformation of CW, the group algebra of the finite Val group. So there are in one-to-one correspondence with irreducible W representations. So by abuse of notation, I will denote by res WV the W possibly reducible W representation that corresponds to this res K V. Okay, so now I need one more ingredient. In order to formulate it, so this goes back to the work with Dan Barbash and Peter. This is the so-called pin cover of W. So what I do is fix a positive definite form on TR, such that W invariant form on TR. So that W is a subgroup of the orthogonal group. And now you can form the Clifford algebra, this form. So I won't write the definition, but inside the Clifford algebra, inside the group of units of the Clifford algebra, you have the pin group, which is a double cover central extension by Z2 of this OTR of the orthogonal group. And then you pull back W, so you get this W tilde. This is the spin cover. Okay. And what plays a role is not the irreducible representations of W, but the genuine irreducible representations of this double cover. So these are irreducible representations that do not factor through W. Okay, so what are they? How do you classify them? So there is a case-by-case classification due to Morris from 50 years ago, but then recently part of this work with partly with Ciubotaru, we found a different classification that's more like a Springer type classification. So in order to state it, remember that the Springer correspondence, you can think of it as a surjection from the irreducible representations of the Val group to these nilpotent orbits, and the fibers correspond to these local systems of Springer type. So this pin Springer correspondence that we found, so this is with Ciubotaru, says that the irreducible genuine representations of this double cover are roughly parameterized by nilpotent orbits of a certain kind. So this N check sol, these are nilpotent elements such that the centralizer in say, the Liealgebra of Echec is solvable. And the fibers are, it's harder to, I need more notation to make this completely precise, but roughly the fibers are still parameterized by Springer local systems. So for example, if W is Sn, then the Springer correspondence says that the irreducible representations of Sn are in fact in one-to-one correspondence with partitions of N, where you think of partitions as being Jordan blocks for a nilpotent orbit. And these other ones, they're going to be subjective on partitions with distinct parts. And the fiber is one sign self-dual representation, where a sign is the usual sign of the val group pulled back to a non-genuine representation of W tilde, or two sign dual representations. But the point is that only certain type of nilpotent orbits occur here, not all of them. So for SN, these ones with distinct parts.
So it's like certain representations of the alternating group, it seems.
I don't, is that? Yeah, I forgot now how exactly these are related to alternating groups. I think if you want to get rid of this dichotomy between sign self-dual and sign dual, you need to define what are they called? Super representations. You need to think of the Clifford algebra not as an algebra, but as a super algebra. It has a Z2 grading, and then define Z2 graded representations, and then I think that takes care of this dichotomy. And then you'll just have a unique representation in each fiber for SN.
Maybe I can ask you, sorry to bother you all
Yes.
the time, but about the previous thing that you mentioned. So you looked at the level 1 invariance.
Yes.
And if you look at the Iwahori fixed vectors, that's isomorphic to the Jacquet module as a vector space, at least.
That's right.
Now you look at something bigger. I just wonder whether it has something like the Jacquet module, or something bigger that you can relate to it. I don't know if it's meaningful.
That's a good question. You mean if I take fixed points under some other group in the filtration of K, not?
No. What you took, the level 1 subgroup.
Okay.
Whether you can somehow relate it to either some Jacquet module picture, so to speak.
Well, I mean, yeah. If you take some depth zero representation rather than an Iwahori spherical representation.
No, even for these subquotients of principal series. Either some generalization of the fact that the Iwahori fixed vectors is the same as the Jacquet module. Can you see something at the level of level 1 fixed points?
I don't know. Yeah.
So can I ask also a related thing? This restriction that you define, is it the same as, like, if you think of the model as a affine Hecke algebra model, then is it the same like restricting to the finite part?
Yeah, but that will still be that's exactly right. But that would still be a representation of the finite Hecke algebra. So what you want to do is sort of send Q to 1,
Yeah.
which is something you can do for the modules that I will consider.
Okay, thanks.
And a better way is to think about to go one more step from the Iwahori Hecke algebra to the graded Hecke algebra, and then it really is honestly just taking the restriction to the Val group. Okay, so then let me call this map theta. And let's call theta. So recall that there is a unique maximal nilpotent orbit, O check regular. So in the fiber of that, I have either one or two representations. Those are, this is either one or two spin modules. So I'll just denote them by S. I won't, the one or two has to do with the dimension of the underlying Cartan subalgebra that I took. But these are in fact, these are the simple modules of the Clifford algebra. Okay, so the theorem, which is just rephrasing the result from this older work, is that suppose V is an irreducible unitary subquotient of x nu. Then nu, so the norm of nu, I remember I fixed a positive definite form on TR, nu is in TR. Check. Is less than H check O check over 2 for all O check in this type of solvable centralizer such that there exists sigma tilde in the fiber over that with home W tilde sigma tilde in the restriction of V tensor S is not zero. Okay, so there is a lot to parse, but it's actually a lot easier than it looks. So there is this annoying but important thing that you have to go to this double cover because of the way the theory works. But suppose you didn't have to. All this is saying is that you look at the restriction of V to W, you collect all of the W types that occur in there. Each one of them gives you a nilpotent orbit, and then the nu has to be less than the middle half of the middle element for each one of those nilpotent orbits. Okay, so I take my module, I restrict it to W, I tensor it with the spin, I collect all of the irreducible constituents. Each one of them gives me one of these special kind nilpotent orbits, and then nu has to be less than that. And there is a further.
I'm a bit confused. I mean, as you said, there's a lot to parse. So the O check, I mean, I just want to see the relation to the nu. What about this H hat of O check? Does it show up here? This one, but
this is H check is attached to O check. It's just half of the neutral element of a Lie triple for O check.
So maybe you can say it again. So you start with your V and do this restriction.
Start with your V. You compute this parahoric restriction. You take the corresponding Val group, irreducible representations of the Val group. I need to turn them into representations for this pin cover. That's why I'm tensoring with S.
Okay. And what is this?
Now, sorry, yeah, this is just this parametrization that I alluded to. To each genuine representation of W tilde, I attach in some precise way, not case by case, one of these orbits.
Excuse me,
Yes.
why is your inequality independent of the choice of the norm or the positive definite form on TR check? Or you want it to hold for something?
Well, I mean, both sides depend on that. So it's,
Yeah, but
that-
there may be constants involved. You can't have an exact inequality like that. You have to bring in constants. Even if the norms are equivalent, it can't be just the same inequality in the two different norms.
Norm is unique up to scalar.
No, I'm saying that form you chose, that is not unique, right?
it's unique up to scalar. I mean, if these are,
Oh, it is unique up to a scalar of modulus 1?
No, but you use the same scalar for the left-hand side
For
and the
both
right-hand
sides. You
side.
choose the same scalar on both sides, right?
yes.
Okay, then it cancels out. Okay, thank you.
Don, can I ask,
Yes,
Oh.
yes, sure.
this tensoring with S, can you say approximately what that does to the associated nilpotent orbit? I mean, you start this, I mean, a constituent of this restriction of V corresponds to a certain nilpotent orbit by Springer. And now you tensor with S and you get a special kind of nilpotent orbit. Can you say approximately how those are related?
Yeah, so I mean, there is this, yeah, let me try to, right. So here's the easiest thing, well, the best thing I can say. So suppose sigma is an irreducible representation of the Val group. Then I attach by Springer, this is going to be in the top cohomology of some variety for, sorry, the Springer fiber over some E check. And now, instead of taking the top cohomology, you take all the all cohomology groups. But I want to take them, turns out you take them all alternating like this. And then when I tensor this with S, this is essentially this sigma tilde for O check if O check is if O check is in this N check sol and is 0 otherwise. So what I need to do is, if I start with a sigma, I need to write it as, I need to write it in terms of so it's going to be some sum. So let's give a name to this. Let's call this Y of B, E, check. And, you know, there is some local system that corresponds to some representation phi. So this is this alternating W representation, virtual W representation. So you can, if I have any sigma, then I can write it in the basis of Y's. So we know if I don't take alternating sums, if I take the usual, the entire cohomology, then I know I can write an irreducible representation in terms of these sort of standard modules. So I just want to put in this twist by -1 and write every irreducible representation of W in terms of these twisted standard ones. So then there are some coefficients here. And then when you tensor with S, but the point is that we know by Borel-McPherson that all the E's, or let's call this E1 because they're different. If this corresponds to an E check, all the E1s here, they're going to be greater than E check, if I remember correctly. So then when you tensor with this, you get in here everything that's not in the right-hand side, that's not one of these ones with solvable centralizer will get killed. So roughly, so in here, you have sigma tilde for O check in and sol greater than the nilpotent for the Springer nilpotent for sigma. So you'd like to say that it's sort of the first, usually it's the first nilpotent orbit greater than the Springer one that has this property of being having this solvable centralizer.
What is the subscript phi? I mean,
which subscript?
Then the phi on top, that superscript.
Yes, that's the so you take the centralizer of E check, the component groups of that, and then you take a representation phi of the component group. So that's part of Springer.
Okay. Thank you. Yeah. If sigma, which is a representation of the usual Val group, corresponds in the Springer correspondence to one of these solvable kind of nilpotent, then that's the one that you get in sigma tilde. And otherwise, you have to go up in the closure ordering. Okay, so let me explain some applications of this now. So if you look at this inequality, then in particular, it tells you that you can't have any unitary subquotients if the length of your parameter is greater than the middle element, half the middle element of the largest nilpotent orbit. That's so. Applications. So the first application is if nu is greater than half of the regular orbit, 2, which is also rho, then no unitary subquotient. So this is a classical result, I think maybe due to how and more in this setting. Also immediate is that if nu is exactly that, then if you trace through the conditions that I wrote there, then you see that the restriction of V to W can only contain the trivial or the sign of W.
which then implies that V must be the trivial or the Steinberg representation. So this is another old result due to Kasselmann. Okay, but then we can improve on that by working a little bit more. Now suppose G check is simple, then the nilpotent cone has some structure like this. You have the regular nilpotent, which is always there, even if it's not simple. But then the simplicity implies that there is a unique one just underneath, so the subregular. And then we get that if nu is strictly greater than half h of the subregular over 2, then the only unitary subquotients are the trivial and Steinberg as in 2. So there is nothing in between. And you can see if you look at this condition, never mind this complicated stuff, it tells you that if nu is less than h check for the regular, the next jump is h check subregular. So the only way nu could be greater than h check subregular is if it contains a very small number of W representations, namely the trivial and the sign.
What happens if nu is one of the special h's? Then you know the restriction?
No, so the strategy is that for each O check, I can make a list of what are the allowable W representations for that. And then I impose the condition that my representation of G, this W restriction, has to contain a subset of those. But then if I'm out there are very few W representations that can contribute. So that gives me a way of saying what modules I can have.
But if it's just one of the special ones, you don't know, it's not irreducible. It's not just this one special sigma that belongs to the orbit.
No. I mean, the sigmas, you have more and more as you go down, because if you're at every step, you're allowed to have the ones above. So it's more like having a set of the ones that are not allowed. And then you rule out unitarity by saying that this module contains one of these non-allowable representations. And then I can work a little bit more if the rank of G check is greater than 4, I think. And then I think it's 4. Yeah, then I can show that the only unitary subquotients with are at H check subregular over 2, and they are tempered, and they're the duals. Well, except if G is SO2n plus 1, then there are two more. And then you know, you can go down a little bit more with these methods. If G is not special orthogonal, I can go down one more. There is this regular, subregular, and then there is one more like this we might call subregular, and then after that it becomes crazier, and then we can unitary. These. And they're always like this, either tempered or anti-tempered or some endpoints of complementary series. But the point that I want to make is that at H check regular over 2, there are 2 to the rank irreducible subquotients, and only 2 are unitary, is what we knew from Castleman already. But then something similar happens for the other ones, the subregular and then the subregular. Again, it's like roughly 2 to the rank irreducibles, but then fewer than 8 are unitary. So there are very few unitary representations, as you might expect. But yeah, so I think I'm probably out of time. There are some other applications with respect to complementary series. Namely, I think this method is useful in order to show that certain representations do not allow complementary series. But maybe I'll stop here, see if you have some other questions.
So these last less than or equal to 8, these representations are all tempered or non-tempered?
So they include the tempered ones, the dual of the tempered ones. So there is this operation that I explained. Erez asked me about it. This Zelevinsky involution that is known to take unitary representations to unitary.
Okay. So
they usually, for these larger orbits, then the unitary representations come in pairs because of this. Okay. So there are the tempered ones, the dual of them, but then there are in some examples there are also others that are not like that. So I think if the group is simply laced, then tempered and anti-tempered are the only ones, but for something like SO2n plus 1 or SP2n, then you may get some endpoints of complementary series.
So the number is necessarily even, the number of constituents?
Yeah, it's even for these.
Okay, okay. Thank you.
Or at least if the rank is greater than or equal to 4. I mean, for something like rank 2, you might get coincidences that something is self-dual with respect to this involution.
Thank you very much.
Thank you.
Further questions, please.
So you said you have something about the isolated representations?
About?
Isolated representations?
Yeah. What kind of representations?
Isolated.
Yeah, so I mean, this is what, okay, let me show the picture of G2. I mean, this is, David did this for real groups first, but it's the same picture for p-adic groups. So this circle, yeah, this is where this is the circle that corresponds to the length of rho. So that's the length of the regular that you attach to the regular nilpotent orbit. So the result says that there is nothing unitary outside. Says that on this circle, the only unitary ones occur exactly at the translates of rho, and then you have the trivial and the Steinberg there. And then it also tells you that there is not, once you're inside the circle, there is nothing unitary here until you get to here, to the subregular. And then you're on this subregular circle. And it tells you that the only unitary ones are at the translates of half h for the subregular.
That's what in the appendix of Langlands, right? I mean, the chapter 7 of Langlands at this point.
Yeah, I mean, yeah. Sorry,
in the Langlands book on isotope series, in the chapter 7 or the appendix, he considers, I guess the appendix, he considers G2 and worries about residual spectrum, and I think these points are.
Okay, yeah. So, but what I'm saying is that this picture is true for all groups, not just for G2. I mean, I don't know how to draw anything else than G2.
Understood.
But it's, so by isolated, it's, you know, I mean, the trivial representation being isolated, that we knew that's this Kazhdan property T. But what this is saying, I think, is that if the rank is greater than 4, then the minimal representation is also isolated. And so there is also, you can have a little bit more than the Kazhdan's property T. But the method, I mean, in order to be able to keep track of the computations, you need to have some good understanding on this and some fairly easy structure of the closure for nilpotent orbits at the top. And you do have that. I mean, once you go down, then it becomes more and more complicated, and it's, you know, fairly difficult to keep track with this. But I think there is some more mileage that one can get with this method, with complementary series, as I alluded.
Any further questions?
And then, so I have a question. So here, basically, you consider those Dirac operator in orthogonal sense, but I think you have something like symplectic Dirac operator. Do you get any new inequality or new information?
Yeah, that's a good that's a good question. So I'm sure I haven't studied too intensely, but so far the little bit that I study, I didn't get something so useful as this. But maybe somebody else, I mean, you know, this type of symplectic Dirac operators, the idea was around for a long time, and I'm sure people thought about that, and I don't know any direct useful result for unitary representation.
But there's still the Wogan conjecture is still holds there, or is that something?
That's a good question. I don't know what the right. I think the problem is I don't know what the right formulation of that conjecture might be in that setting. Yeah. There is something that's I think Huang and Panzic did, but to me that's still not. It wasn't really symplectic. It was sort of, in a way, still fake orthogonal somehow. In a way, I don't know how to say it, but I just.
Okay.
Yeah, so it's just a construction at this point that's looking for an application.
I mean, one obvious application is there is a spectral gap, of course, that you exhibit.
Yeah, no. He was asking about, yeah, sorry. I mean, this does this Dirac inequality that I explained does have applications. I mean, this is a nice application, this type of gaps.
But I'm wondering, so there was a lot of work in the past. I remember that and maybe others, they try to explicate these exponents in property T in order to get some nice spectral gaps. So this gives certainly more uniform approach for that, if nothing more.
Yeah, so I should look. I don't know about that. Yeah, definitely. I mean, this once you have the work that we've done with this classification of the irreducible genuine representations of W tilde in terms of the Springer correspondence, then this is uniform. These gaps, and you can push them more. So the type of another application that I really like is to say that certain representations do not afford complementary series. So for example, if I take an irreducible tempered representation that's parameterized in terms of Kashdan-Lustig by one of these nilpotent orbits with solvable centralizer, then it's an immediate consequence of the theorem that I wrote that there is no complementary series off of it. So of course, if you take the zero orbit and you take the tempered representations attached to the zero orbit, that's the full unramified principal series, then you have, for example, for the SL2, you have this Stein complementary series. But if I take tempered representations attached to these bigger orbits, then there is no complementary series off of them. And that's and I think you can try to generalize those type of results with the Dirac inequality.
Any further questions? If not, let us thank Dan again.
Thank you.
And next week, our speaker for next week is Anna Maria Albert. I do not yet know the topic. You're welcome to say it.
Yes, it will be about C-star blocks on of temporal representation of group over local fields, so p-adics and real groups. So I will send you a title. And that's
Thank you very much.
Thank you.
So see you next week. Everyone is welcome.
Thank you.
Bye.
Thank you. Bye-bye.